Hello, welcome to this course on photonic integrated circuits. Today we are going to get a brief introduction about photonic integrated circuits. What are these photonic integrated circuits? Why do they create a lot of enthusiasm among the recent technologists? Let's dive in and look at what they are actually. So integrated circuits or integration, right, on chip has been a philosophy for microelectronics over the past couple of decades. Right. So the whole idea of integration coming from realizing bulk functionalities. Right. So you have various components that you see on the left side. Right. There is an oscillator. You have passive elements, resistors and capacitors, all in a circuit board. This is a printed circuit board. Right. But then if you want to miniaturize this and if you want to increase the functionality, the best way forward is make it on a single flat substrate. So that is what we call a chip, and there are reasonably thin substrates, right, and all the components that we saw here, they are all miniaturized. They are now very small. So from you are going from millimeter scale here to micrometer scale here, in some of the cases nanometers. So this miniaturization brings in a lot of advantage. So the integration of all these components is going to bring functional enhancement and also performance enhancement. So that is what we strive for any system currently we have. We would like to increase the functionality. See, if you look at mobile phones, right. So mobile phones from generation to generation, we are looking at various new features adding in. Previous generations are slower than the current generation. We have more memory, right, and much faster. So how do we achieve this? This is all through integration. And now we have more functionalities. So we started with one camera. So now we have 3, 4, right. So the cameras are increasing, but then your sizes all remains the same and it is getting faster. So on the one hand you are increasing the functionality. Now you can measure the pressure levels. Now there are very smart biosensors integrated onto your mobile phones as well. So the functionalities are increasing. The performance is also increasing. So how do we achieve this? This is all through what we call integration. So instead of having one processor board, right, that is addressing, let's say, one camera or one sensor, and now we have 10 sensors all addressed by a single processor board. So now this integration, as I mentioned, is going to be the key going forward with advanced technology. So that is all about how and why we need to do this, right. And the next thing is understanding what this integrated circuit is. For some it might be trivial, right. For people who have done electronic integrated circuits, it is very easy to understand what this integrated circuit is. But then the integrated circuit in conventional sense, right, is nothing but to put together in a desired fashion. So individual components are put together in a desired fashion to achieve a desired functionality. It is a very important philosophy here. So you are going to have multiple components. So these components, for all practical reason, we can consider like resistors, capacitors, right, that we understand. Right. This could be also other components, right. I am not very specific about electronics, but maybe I have something to do with race cars, right. So you also see this individual components, right, in those racing circuits, and that is the reason why we call the racing circuit, right, instead of saying it as a track or a road, right. So it is called a circuit. The reason for that is if you take a racing circuit, right, you have various aspects to this racing circuit. So you have a very tight bend where one need to slow down, and there is a straight section where you demonstrate straight line speed, right, and how you maneuver here, right. So this is all various components, and you want to put it in a desired fashion in order to make this as a closed circuit, right. And then another interesting thing is to look at how we can put resistors and capacitors together, right. So, how do we do that, and you have to put it together in certain fashion, right, so that the functionality is something desirable, all right. So, you cannot randomly connect things and call it as a circuit, right. So, it has to be connected in certain desired fashion to achieve desired functionality, all right. And electronic circuits, to be specific here, so that we have familiarity. So, discrete components. So, this discrete components are resistors, capacitors and inductors, let us say, or individual circuit blocks, right. Circuit blocks could be amplifier, for example. So, amplifier is a circuit block resulting in a desired or global functionality, right. So, you want to realize a global functionality, you want to put this discrete components or individual circuit blocks together, right, in order to make a circuit. And if they are all going to control the flow of electrons. So, all of this, why are we doing this? We are going to control electron flow, right. So, we want to control electron flow using this circuit, and this is what we call electronic integrated circuit, right, or there is large scale integrated circuit, very large scale integrated circuit, ultra large scale integrated circuit, right. So, all these comes under the class of controlling electrons through circuits, right, arranging various components in a certain fashion. But then what is a photonic integrated circuit? Can I use the same philosophy? Absolutely. So, what you have here in a photonic integrated circuit is you have discrete photonic components or optical components, and you also have individual circuit blocks. In this case, the circuit is controlling the photons to some extent, and this is all resulting in some global functionality, right. So, this global functionality could be for example a filter. So, you want to filter light, okay, and here the discrete component could be a mirror elements, and we also use lens, right. These are all discrete components, and individual circuit blocks. What could be a circuit block when it comes to a filter? It could be an interferometer. So, interferometer is wavelength selective, right. So, that is a small circuit. So, having all of this together, we call it as a photonic integrated circuit, right. So, this mirrors and lens, this is all in bulk sense, right. So, you have very large mirrors, right, lenses that you have, and you might also have mirrors, reflecting mirrors, right, and you have lens systems, right. So, these are all bulk in nature, right. So, what we would like to do is we want to miniaturize, we want to make a circuit out of it, similar to what we saw earlier. A discrete resistor now sits on a chip, right. So, now how do we convert this lens, right, or mirror, right, how do we bring that onto a chip? We have to reduce the size of those devices. What is the physics behind those reduction? Are there any limits to it? And that is what we would like to understand in this course. So, in order to understand how to convert this lenses and mirrors into circuit, let us look at how do we guide light, right. So, we have to make sure you take a photon or light from point A to point B. So, we want to understand how we can do that. So, we can easily do it by using lenses, series of lenses, and that is the example that you have here, right. The cartoon there shows you how one can take a lens, right, and then arrange it in series, so that you can take light from point A to point B, right, and this is all in a straight line, right. So, if I want to bend this light, I can also do that. We will look at it shortly, okay. and instead of lens, so lens is a transmission or transmissive, right. So, you are doing this light propagation from or guiding from point A to point B by transmitting is through the lens here. Okay. You can also do it by reflection mechanism, right. So, through reflection, so you can put mirrors. So, I have mirrors, right. Light always travels in straight line, we know that, right. So, I can put mirrors and then make the light reflect these position, and I can take the light from point A to point B, right. So, these are all very simple way of looking at light transport from one point to the other point. So, this might look like pretty trivial, but I can also realize light going from point A to some other point B here. So, there is an obstacle here, let us say. So, there is an obstacle. So, I cannot do line of sight. So, normally what we do is you can do line of sight and light can reach point A to point B, but now I cannot do this, right, because there is an obstacle. So, there is an object sitting in between, all right. So, how do we do that? So, we have to go this way, right, and put a mirror and then take it to point B. So, this is how we can realize this light transportation. So, now we need one additional element, right. So, there is a mirror required here. Again you can see here it has to have a complete straight path here without any obstacle, right. But then if I say okay, I have to do this light transmission not in free space, but underground. How do we do that? It is nearly impossible to think about having all these mirrors underground, and that is where we use optical fibers. So, you can use optical fiber in order to transport light without worrying about what is there in the atmosphere. So, this is optical fiber. So, the optical fiber will help you to transport light from point A to B without having any difficulty, right. And the light transport there also happens through reflection, right. So, light inside is getting reflected. So, let us look at how it can go. So, it is getting reflected inside, okay, and it follows a principle called total internal reflection, right. So, this is the principle that we use, similar to mirrors. So, the light is getting reflected within optical fiber, right, and confined inside without escaping outside, right, without escaping to the environment, and this is taken care by a phenomena called total internal reflection that mimics mirror like behavior, all right. And this is how you can transport light in a denser medium, okay. So, you take optical fiber which is denser, and you can also take silica slab, right, like our mirror we have. So, you can take a mirror and then make light propagate through this mirror. So, these are all the ways to guide light, all right. So, let us look at this total internal reflection. We discussed about how to keep the light inside the denser medium, right. So, we all understand light reflection and refraction, all right. So, this is something that you might have learned in the introduction to photonics course. So, when you have light inside this medium, so it can refract and it will also reflect, all right. There are two processes that happens at the interface. So, when the refractive index of the medium where the light is sitting is higher compared to the environment, all right. So, this phenomena will happen, but our idea is to keep the light inside, we do not want this refraction, okay. So, how do we achieve that? This can be done by changing the angle. So, we have this angle here, right. So, that is the incident angle. So, when you change the angle of refraction also changes. So, it comes closer and closer. At a particular angle, what we call the critical angle, right, the light reaches nearly 90 degrees, right. So, it makes 90 degrees with the normal here. So, that means the light is propagating at the interface between the higher refractive index and the lower refractive index medium. And this is a really an interesting point, right. Beyond this angle, all the light is reflected inside, and that is what we call angle of total internal reflection, right. And based on this principle, we can confine light inside the medium. So, there is no light escaping, right. And the way that we can understand this by from our Snell's law, right. So, we studied this sine inverse of n dash over n, right. So, this is how you can find what is the critical total internal reflection angle. The moment you know the refractive index of the material inside and what the material is outside, you should be able to find what is the critical angle beyond which I can keep the light inside. And this is how all the guiding wave principle works. So, when you take optical fibers, this is the principle. So, single mode optical fibers, multimode optical fibers. So, there is a concept of light confinement inside, right, and this confinement is through this total internal reflection. Not only for fibers, later on we will just see that even in photonic circuits that we do it on plain flat surfaces, you can still use this total internal reflection principles. Okay. Let us move on to look at optical fibers. So, optical fibers, we all know it is a glass material, right, and it consists of two material system, one is core and the other one is cladding. So, the core is the one that is at the center, and for a single mode fiber the refractive the diameter is about 9 micrometer, right, and the refractive index we call it as n core, right, and then outside cover is called cladding, right, and the refractive index of that cladding material is n clad, and the diameter is roughly about 125 microns. So, this is almost thickness of your hair, right, slightly larger. So, the important condition here for the light to be kept inside the core is n core, that is the refractive index of the core should be greater than the refractive index of the cladding, alright, and only then we will have this total internal reflection. So, this image if you remember we already saw, right, at a certain input angle, now all the light is confined, and I can at a particular incident angle this light is going to stay there forever, right. So, it will keep on bouncing back and forth, okay, without any loss. So, this is the reason why you can make optical fibers of kilometer long, right, yet without any appreciable loss. We are talking about 0.02, 0.01 dB per kilometer, right, very small loss. So, all the energy is confined inside. This is very essential. The reason for this is you are going to communicate to somebody who is sitting, or servers that are sitting tens or hundreds of kilometers apart. So, you are watching this video right now, and this video is streamed from a server, it could be 100 kilometer, it could be 1000 kilometer from where you are sitting, right. But this information is now traveling through this optical fiber, right, and this optical fiber should not lose this signal, and that is the reason why the loss of this signal should be very low, and this total internal reflection is one of the reasons why you are able to transport photons with very low loss, alright. So, that is all about how we propagate light through optical fibers and through this total internal reflection. Let us look at how things are in a planar waveguide. Right. So, optical fibers are nice, we understand it very well, but our interest is to make photonic circuits on a chip or in a flat surface. So, there you cannot make circular geometries, right. So, there we are looking at rectangular type waveguides or structures. So, you know the condition still remains, your refractive index of core should be greater than refractive index of cladding. Okay. So, this is the condition that should be satisfied. So, now we have a core material here, right, and it is surrounded by a cladding material. So, we can say top cladding and bottom cladding, right. So, for general purpose I have mentioned that top cladding and bottom cladding, two different colors, but it can be same material as well, right. So, it can be same material. So, the material can be same or different, but the N clad top should have lower refractive index than N core, right. Same thing is true for N clad bottom should be less than N core. So, this condition should be satisfied. So, your core refractive index should be greater than the surrounding mediums. So, one should keep that in mind, all right. So, they can be different, the top and bottom can be different, but then they should be lower than the core refractive index. And while understanding this, let us look at two different type of waveguides we can have, planar waveguides that you can have, right. So, this is all cross section, this is a cross section of the of a waveguide. Let us say this is x and this is y and this is the propagation direction, right. So, this is z. Okay. So, this is the propagation direction. So, when you have a rectangular structure like what you see on the left side, we call this as a strip or wire waveguide. Okay. So, wire waveguide, it is similar to electrical wires, right. So, the wire lines that you have in your PCB board looks similar. So, they are rectangular in nature and they can guide light. All right. On the right side what you see is a partial removal of material here. So, you see a slight step here. So, the material is not completely defined as a wire, but you have a shoulder on the sides, right. And this structure can also propagate light. So, confine and propagate light, and this structure is called a ridge waveguide. All right. So, once you have this two different structures, we need to understand whether light will propagate through this. There is no need for you to believe that when I say this structures will confine and allow light to propagate, right. So, you should question that. So, why do you say that? So, how can we believe that light would propagate through this structure? And that is where our good friend Maxwell comes in, right. We have studied about Maxwell equations in our basic courses like Introduction to Photonics. And in that course probably you must have understood that in order to define an electromagnetic wave, we need to understand the four golden equations and then a wave equation that represents light, right. So, we take advantage of those definition and then solve this structure, right, to see whether light will exist in this particular structure, and if you do that, this is what you get, right. So, what you see the two images at the bottom are nothing but the intensity of light when you do Maxwell solution to when you find the Maxwell solution to this structure that was represented with the two cartoons at the top, right. So, light is nicely sitting at the center, right. If I do a cross section of it, it will look something like this, a nice Gaussian profile. And similarly here as well you see light sitting in, right. So, from the Maxwell solvers, or you can do it analytically or you can do it numerically, you can find whether light will be guided in this, right. So we will look at how and so on later part of the course, but indeed you can find take any structure and find whether light will be guided in this, and based on the solution you can say whether I can use this structure for guiding light. Okay. You can come up with any kind of geometry, right. So we said we went from a circular geometry from the fiber to a rectangular geometry here, and you can think of some triangular geometry, let's say, right, or a trapezoidal geometry, right. You can be as creative as you want, right, but then there is a boundary condition to that creativity, right. It can be geometrically looking nice for you, that okay, I can put light into this particular structure, but then you have to ask Maxwell for that. So the Maxwell will tell you whether that particular structure you came up with will guide light or not. Okay. So those are all the things that we will look at in the introduction or refresher that we are going to have on the electromagnetics. So why are we really interested in this photonic circuit, right? So we said we can confine light, okay, and we can do light propagation through this structure, right. What is the use of this, right? So the use of it comes from various applications that are really impactful and disruptive. So just to give you a few motivation why this photonic integrated circuits are really good, in this particular slide I just compiled what could be interesting. So photonic integrated circuits is a disruptive technology, and it leverages matured CMOS infrastructure. So fabrication of these structures are very important. The circuit fabrication are very important, similar to microelectronics, where all these chips are made in huge microelectronics foundries. We want to make sure this photonic circuits should be able to be fabbed in such large establishments or infrastructures. So using those infrastructure, can we fabricate our circuits? And the answer is yes. So we can do that. The next thing is material. So invariably almost more than 90% of circuits are made out of silicon, right. So you say 90%, what happens to the other 10%? There are other RF applications where people use 3-5 compound semiconductors. It could be 10, it could be less than 10, right, depends on the application domain that you are looking for. But then when you look at the processors, right, that we use in everyday life, it's 100% it's all silicon, right. But then there are application in high frequency and so on where people use compound semiconductors. Similarly, in photonics we have silicon, we can use silicon, and silicon alloys as well, silicon nitride, silicon carbide, silicon oxynitride, and silicon based compounds. For example, germanium could be used there as well, right. So all CMOS compatible or microelectronics compatible materials could be used, and also compound semiconductors, right. So when you say compound semiconductors, gallium arsenide, right, indium phosphide, basically 3-5 group elements. So if you make alloy out of it, we can make use of those technologies as well. Because of this richness in material technology, it is highly scalable. The mature technologies are available, and you can do monolithic or hybrid integration of devices and material technology. So it gives you a lot of versatility in this platform, right. And above all, photonics is EMI and EMC free. So that means you can use it in very harsh environment where you have radiation, where you have a lot of interference, right. And also it is high speed, right. So light travels at the speed of light, there is no contest there. So you can communicate information very fast. And also the interesting thing is, unlike electronics, you can do parallel processing, right. You can do a lot of information sharing in parallel, right, because of wavelength that you have, right. So just to summarize, you can have versatile platform, high speed, you can do a lot of signal processing at high speed, and then you can do sensing as well. Using light you can probe information. Okay. So, those are all real application of photonic integrated circuits. And the next important thing is, how small can I make these circuits, right. So, this is a very important question to answer, right. I am making a circuit. So, how small a circuit could be? We are primarily limited by the diffraction, particularly a guided wave system, right. So, we all know, the wavelength of light inside the medium depends on the refractive index of the medium. So, the wavelength of light inside the medium is profiled by the refractive index, right. So, that is lambda naught, which is the free space wavelength divided by the refractive index of the medium. So, just to give you an example, a 1550 nanometer light source or wavelength of light inside silicon, right. Silicon is 3.45, that is the refractive index of silicon. The wavelength inside the material is 450 nanometers. So, now you can see we had 1.5 micrometer of wavelength, right, in free space. So, now when you put this light into silicon, it becomes 450 nanometer. So, we can squeeze the light by just choosing a high refractive index material. Then for some of you might be thinking, oh, if I put 1550 nanometer light into silicon, right, then my wavelength goes from 1550 to 450. Can I do wavelength conversion, right? That is the question that probably pops up, right, but you cannot do that. The reason for that is the wavelength or the color is frequency dependent, not wavelength. Wavelength is a representation in space, right. So, frequency is what you should do to understand colors, all right. So, size depends on the wavelength of light and the medium that you are propagating, and this is what gives you the confinement. Okay. How small can you do? And you want to think what are all the type of devices that you can make in this photonic circuit, right. So, what do you need? You need a light source to generate these photons, right. And then once you generate the photons, you want to couple, let us say out to the outside world or even within. So, you need a good light chip coupling, right. So, once you have the coupling done, then you want to have a waveguide structure, right. So, that can guide the light wherever you want. So, you go from point A to point B inside the circuit. How do you do that, right. So, that is using waveguides. So, that is another component there. And then wavelength selective filters, this is an excellent property or really amazing property of light compared to electrons. It has wavelengths, right, and these wavelengths, they do not talk to each other, they will not share energy, right, in a linear sense, right. In non-linear photonics, that is what you try to do, but in linear low power world, these photons will not share energy. So, they will hold on to the information they have, right. So, you can send in multiple wavelengths in parallel, and how do you discriminate these wavelengths, and you need a wavelength filter for that. And next is a light modulator, right. So, how do you change the properties of light, right. So, if I want to change the intensity of light, right, and this intensity of the light change should be correspondent with an electrical signal. So, I want to transmit an electrical signal through an optical fiber. How do I do that? So, I have to change the intensity of light that should correlate with change in the electrical signal, and that is what you do with light modulators. And then the next thing is how do you detect light? So, I want to convert the photons into electrons, right. So, how do you convert that? And that is what photodetectors are all. So, now you have this toolbox, and all of this I want to be present on a chip, right. So, this is the whole philosophy of having photonic integrated circuits. So, all these components, all these elements, all these functionalities should be available on chip, right. So, that is the main idea of this course. We will understand each and every component and then see how we can put it together to realize really fascinating applications, all right. So these are all some of the images of these devices. So let me wrap up with going through the course outline, what we are trying to do in this particular course in the next 12 weeks. So we will start with a brief review of electromagnetic waves, so that everyone is up to speed, right. So some of you might have done this electromagnetics long time ago, and we will make it very specific to this course, right. We are not going to look at whole electrodynamics, so we will look at what is appropriate for this course. And then in the next week we will look at a brief introduction about the circuit. So what is all this photonic integrated circuit is all about, each component, what they do and how you can exploit that. And the next thing is material technology. So what kind of material one can use and how do you grow this material, right, how you can use and exploit this material, particularly for integrated optics. And next we will look into the guided wave optics. How do you guide light in the circuits, right. So we will look at the guiding mechanisms, right, and then we will move into design of this waveguide. So how do we design a waveguide within which you can confine and propagate light, and how do you couple light, right, between two different devices on chip, right, and also how do you couple light between optical fiber from the external world into your chip, right. And we will look at some of the passive components like filters, splitters, and all those passive components. And then active components, meaning here light generators, right. So how do we generate light inside the circuit, and also how do we detect light inside the circuit, right. So those are all active functionalities where we are not controlling light, we are actually changing the property of light, right. And modulators as well, how do you change light property like intensity and phase. So we will look at that in active devices. And then we will also look at semiconductor light source and detector separately, right. So we are going to look at how we can generate light in a semiconductor, how we can detect light using semiconductor, and also how can you put this in a chip configuration, right. And finally we will look at fabrication and engineering of this material for specific application, right. You might be using different wavelengths, right. So the material should be transparent in those wavelengths. At the same time we should be able to make the kind of devices that we want. So what are the fabrication challenges we have in doing so. And in week 11 we will look at some of very specific material platforms. We will look at silicon photonics, we will look at 3-5 photonic circuits, and also we will look at some of the new emerging areas, right, of the circuits that are coming up that one can exploit for various application. And finally we will look at some of the case studies of how to use the circuits for communication and also sensing purposes, right. So that will be at week 12. So with this course you should be able to have a comprehensive understanding of what this photonic circuit is and how you can design various devices, right, discrete devices, and how can one put this together in order to realize a certain functionality, and also look at some case studies of what material that one can use to realize, for example communication application. You are going to transmit data, how can I use photonic circuits to transmit data and also receive data. And the other application is sensing, how I can use this photonic circuit to sense the environment. So this could be gas sensing, it could be fluid liquid sensing, for example, right. So we will take a case study on that. So it will wrap up a complete understanding of this field, which is really emerging, and a lot of interesting things are lined up in this particular technology and also in this course. I hope all of you will enjoy understanding this. Thank you very much.